Welcome to the Room of Lives. I'm your host, Neil. Today's episode is a recording of a public talk by Dr. Aaron Zimmerman, professor of physics at the University of Texas at Austin and researcher at the LIGO gravitational wave detector. And he was also the speaker way back in episode 11. Dr. Zimmerman gave this talk a few months before the eclipse of April 8, 2024. He speaks about how an expedition was undertaken during the eclipse of 1919 to show evidence for Einstein's new theory of gravity. He then talks about the phenomenon of gravitational lensing and the black hole at the center of our galaxy.
So I'm a professor at UT Austin. I study gravitation, gravitational waves, black holes especially, and black holes will make a little bit of an appearance tonight. But this talk is about an interesting effect due to our theory of gravity, the bending of light. So this talk is bent light and black holes, and let's just go ahead and get started. So a big part of this talk is the story of the eclipse. And it's worth going ahead and advertising that we're going to have an eclipse of our very own in not too long. So there is a solar eclipse happening next year, April 8th, 2024. And what's really exciting about this eclipse is we are very close to the path of totality. Now, depending on where you are in the United States, you're going to see different amounts of the sun covered by the moon at the middle of the eclipse. If you're in the path of totality, the moon will completely cover the sun greeting. And now we're at the very, very edge, as is San Antonio. But all you need to go is a little bit north or a little bit west, and you will be in path of totality. So mark your calendars and figure out what you're going to be up to, because I, for one, have never seen solar eclipse. Seems like a really cool thing. This talk is about perhaps one of the most famous solar eclipses, the eclipse of 1919, which happened in May 1919. Just a little while after the close of World War I. And this eclipse was really, really famous because it was used as the first test of a brand new theory of gravity that had been proposed just 4 years earlier by Albert Einstein. So for hundreds of years, our best understanding of gravity as a theory was Newton's theory of gravitation, a theory that stated that different bodies had a force of attraction that acted at a distance, whose strength fell off as the bodies went further apart, but grew as the bodies were more massive. And this theory is spectacularly successful. It explains with incredible precision the motion of the planets around the sun, the motion of the moons around those planets, and even subtle shifts to the orbits of the planets due to the tugs from the other planets in the solar system. But there was a problem with this theory. Albert Einstein in 1905 put forward the theory of special relativity, which was really a theory that's focused on electricity and magnetism. It was a new way of understanding how electricity and magnetism worked. And it was a beautiful theory that sort of tried to set different observers on the same footing. This theory, again, was spectacularly successful. It explained a lot of experimental results that were puzzling and predicted a lot more experimental results to be verified. But it had a strong disagreement with Newton's theory. For example, Newton's theory, as it was understood at the time, would predict that the force of gravity acted instantaneously. But in Einstein's theory, no forces could act faster than the speed of light. It took Einstein 10 years to finally come up with a proposal, a complete theory of gravity, the general theory of relativity, which combined his special theory of relativity with gravity in order to explain the universe as we know. And it really is a radical reimagining of everything we thought you knew about the universe. Einstein's theory of general relativity tells us that gravity is not due to, say, the sun pulling on the earth. That's a great model. It works really well for almost everything you want to do. But the even better picture is actually that space and time itself have a shape. And massive bodies like the sun imprint themselves on the shape of space and time. And the earth really just wants to go on a straight line. But as it tries to move on a straight line, the straightest path it can through curved spacetime turns out to take it around on an orbit in a way that's almost completely equivalent to Newton's theory of gravity. And this can only be really tested by really, really fine, careful measurements. Measurements that at the time Einstein predicted his theory were not really available. The most important post facto evidence for his theory was the motion of the planet Mercury. Okay, so Mercury had long been studied and long been understood to have an orbit that was behaving just slightly differently than Newton's theory predicted, accounting for Jupiter, the sun, all of the other planets, everything that was known. With all kinds of crazy explanations. Maybe there was another planet, Vulcan, even closer to the sun, so close to the sun that our telescope just didn't see it. It was tugging on Mercury and causing a slight change to its orbit. Or maybe there was another Earth, a planet X on the other side of the sun in lockstep with us that we could never see, but that was tied to Mercury. Well, Einstein's theory, when he wrote it down, predicted this motion of Mercury just from that theory. But it was after, it was a post facto evidence for his theory. It wasn't a prediction he had made and that then was verified. That had to wait until 1919. The cool thing about the prediction that Einstein's theory of general relativity bends the path of light can actually be understood from his theory of equivalence, which is actually one of the core ideas that Einstein used in developing his theory. And this is something that we actually can sort of physically understand and have an intuition for. The idea of Einstein's principle of equivalence is that gravity, you standing on Earth, having the Earth pulled down, you on with surface via gravity, is going to be equivalent in every possible way to acceleration. And here, to mimic acceleration, we imagine that you are in your spaceship that we all got at home, far out, away from everything else, and you've got a rocket. And when you fire that rocket, you're not just going to go faster, you're going to go faster and faster and faster. We can imagine what this feels like from our experience in elevators. As the rocket engine fires, the floor presses up into our feet and drives us up with acceleration. Einstein's principle of equivalence is that these cannot be told apart. There's no way, if I locked you in a box, for you to tell me if you were standing on the Earth or if you were in a spaceship that was accelerating, with just the right acceleration to mimic the force of gravity. So if you drop your little ball, which is the experiment that we all as physicists need to do in this situation, you're going to measure the exact same motion for that ball if you're standing on Earth or in the rocket, one, because gravity pulls down, and two, because when you let go of the ball, the floor is going to rush up to meet it. This principle of equivalence goes further. For example, it equates free fall with no gravity at all. So if you jump out of an airplane and we ignore for a moment air resistance, we fly towards the surface of the Earth, you're going to have a sense of weightlessness, as if there were no gravity under at all. We often think about astronauts floating around in orbit around the Earth as in sort of gravity-free environment, but that's just not true. Gravity is now weak on astronauts. Okay, they're away from the surface of the Earth. Gravity is right there pulling on them. So why do they float around? Well, it's because they're constantly in free fall. They're moving sideways and falling to the Earth at the same time in just such a way that they fall forever. And that's the real reason why they experience weightlessness. This idea of falling so that you don't feel the force of gravity can be told apart from you just being in your spaceship, far out space, with your engines off. You're floating away, no gravity whatsoever. They're the same. This is the principle of equivalence. We can bring these together now to understand immediately why Einstein's theory predicts the bending of light by gravity, something that is not necessarily predicted by Newton's theory of gravity, because in a certain sense, you could argue light doesn't have a mass. Or even if you try to argue maybe light's got some sense of mass and so it should bend, you don't necessarily get the right prediction. So let's imagine that I shine a laser light into the window. It moves in a straight line. But now imagine if I redid this experiment while you accelerate. The light moves in a straight line, but you're moving a little bit, and then you move even more, because again, you're accelerated. You're going faster and faster and faster every moment. And now let's imagine, what would that particular path look like to you in your spaceship? It would look like the light was actually bending downward in order to match that faster and faster drop of the light's path. And so we can predict solely on the basis of the equivalence principle that if light bends when you're being accelerated, then by equivalence, light must bend when you're standing on the surface of the Earth. But Not by very much, it turns out. Okay, light moves really fast. The acceleration you need to mimic Earth is not that much. It's really hard to detect. It's really, really hard. So what we need is we need a lot of mass, and we need some way of measuring the bending of light very carefully. And so this is a great idea. We know where there's a lot of mass, not that far away, the sun. I mean, imagine I look at a distant star, and when that starlight passes close to the surface of the sun's much stronger gravity than Earth's gravity will bend it in a curve. And when it arrives at us on Earth, because we're usually thinking about starlight as traveling in straight lines, what you'll think as you trace a straight line map is that that star is over there. Sorry, I'm pointing at the wrong screen. Over there. But the star is in fact there. So there's a difference, a perceived difference, a shift in the sun's location due to the fact that the light arrives on a bent path, not on a straight path. This is a wonderful idea. We can do this right now. I'm going to go look out at the sun. But we run into yet another problem. It's hard to see the stars in the daytime. And I can't wait till night because then I can't see the stars next to the sun. So what in the world can we possibly do to solve our conundrum? It was eclipse. We can wait for an eclipse. And that's what was done in the eclipse of 1919. An astronomer, Sir Arthur Eddington, an English astronomer, led an expedition. There are actually 2 expeditions. I'll get to a beautiful infographic in a second. Led 2 expeditions in 1919. You see, Eddington was a real fan of Einstein. He read Einstein's theory and he really appreciated it. He understood it and he really thought it was beautiful and wanted to see if he could gather experimental evidence for it. He knew that if you could just find eclipse and take good images of stars near the sun while the sun was being blocked by the moon, that you could test Einstein's theory of relativity. Eddington's a really interesting character, and first of all, he was a giant of astronomy in his time. He developed all kinds of awesome stuff. We had things like the Eddington limit named after him that people still talk about all the time in astronomy colloquia, and he helped us understand how stars live their lives and a lot of great things about astronomy. In World War I, he wasn't a particularly popular person because he was a conscientious objector, a Quaker. He was a pacifist at a time when all of Europe was embroiled in a brutal war. Now, he managed, because of his position as an academic, to secure several deferments. But finally, in 1918, his time was up. He was going to be thrown in jail if he didn't go and serve in the war. But the astronomer royal, Dicey, managed to go to his court hearing and argue, well, let's let him lead this eclipse expedition he really loves. And that will be another year's deferment for him, which luckily for him, the war ended before that deferment was over. So he managed to be able to hold to his beliefs and not fight in the war. His was also not a very popular viewpoint because he was now a proponent of reconciling the sciences, right? This brutal war had really pit all of Europe against itself. And in England, it was not very popular to read the works of a German scientist, right? And a lot of people didn't think much of Einstein's work at this time, Einstein being a German physicist. But Eddington wanted to sort of do something to help with this reconciliation and prove Einstein's theory right. And he led these 2 expeditions. One of them was to an island off the coast of Africa, Principe. The other one was to this place, Sobral, in South America, in Brazil. Now, both these 2 expeditions, things almost went wrong, okay? In both locations, it was cloudy, leading right up to the eclipse. The clouds cleared a little bit earlier in Sobral, and they managed to take a lot of good photos. In Principe, it was cloudy right up until the eclipse was starting, and Eddington wrote that he didn't even get a chance to see the eclipse because everything was covered in clouds until just when the eclipse was starting, and then they started to take pictures, and we were busy switching out photographic plates because, of course, they had used photographic plates back then. For those not familiar, right, if you used to develop pictures on film or plates, not on our cameras and computers, it was tough times. And after taking this data and bringing it all together, the goal here was to compare the observations of the locations of all of these stars marked as arrows at the time of the eclipse and compare them to an identical photo taken some months earlier or later when these stars would be up at night instead of up during the day. This was a really good eclipse for this approach because at this time, during the eclipse, the sun was actually in the Hyades, which is a bright constellation. So there were a lot of bright stars to observe. And sure enough, Eddington crunched the numbers and his assistants crunched the numbers, and they discovered that yes, the stars had shifted position. They had not just shifted position relative to their other observations, they had shifted position precisely as Einstein had predicted. And so we see this headline, which I've seen many people given their tasks because it's so fun. The lights always skew in the heavens. Men of science, more or less, macabre over results of eclipse observations. Eddington went around and made Einstein an overnight international celebrity by reporting on these observations and reporting on the wonderful theory that Einstein had put forward to understand gravity. So that was the first verification after the fact of Einstein's theory of relativity. I can tell you now about where the bending of light stands in more modern contexts. We can move on beyond that wonderful eclipse from more than 100 years ago. This is a much more modern picture showing the bending of starlight. In fact, it's showing the bending of light coming from very distant galaxies. This is a picture taken not that long ago by the James Webb Space Telescope. I think it's the first picture that was unveiled as part of a press release by the president advertising all of the amazing new science the James Webb Space Telescope can do. I didn't have time to put up an image of James Webb Space Telescope, but it's a brand new space telescope, many, many years in the making, which has an enormous beryllium-coated mirror. Its goal is to image extremely far away galaxies. And famously, when we look at very far away things, we're actually looking back in time because the light from those things takes a long time to reach us. So the further away we can look, the earlier we look. And James Webb's goal is to look at the universe at some of its earliest phases and see galaxies as they bulk. This particular picture is taken of a field of stars, and there's actually two things going on here. Well, there's a lot more than two, but the major things I'm going to draw your eye to, in the foreground, there's actually a massive cluster of galaxies. It's enormously heavyweight. Most of it is invisible, okay? Most of the matter in our universe that holds clusters and galaxies together is dark matter. It doesn't shine in light. Behind the cluster, we see other galaxies. And we see that those galaxies, if you look, we actually see those galaxies over and over again and distorted. These sort of smears and arcs of light are actually galaxies that are seen multiple times and heavily distorted. That's because the cluster is creating such a strong bending of light that it acts like a lens, okay, like an actual piece of glass, and the light coming from the background galaxy is being bent in many different directions. And here on Earth, we can see the light coming from different emission directions bent along different paths, which provides us with multiple images of the galaxy. This allows us to learn a lot of cool stuff. We can use this kind of lensing of light to measure the mass of the thing in between. But another cool thing that could be done is we can use this lens just like you use a lens in a microscope or in a telescope. You can use it to magnify things you would not otherwise see. At the center of our own galaxy, we know that there is a truly enormous black hole. It has more than 4 million times the mass of our own sun. And we know that because two different teams have trained powerful telescopes to the very center of our galaxy, and they have watched for years the orbits of stars moving around. And the amazing thing is these stars are all orbiting a center where there's no light, but we can infer from their motions that that center is extremely massive. And you can see these stars, as they get close, they deflect very strongly around that center because of its enormous gravity. Okay, so these are real observations of real stars. So by observing these stars, they can infer, the astronomers, that there is this incredibly massive thing. And by all of the physics we know, it must be a black hole. There's no other way to pack that much unseen mass into one place. But we physicists always like to try to know for sure and develop even better and better evidence for our beliefs. And so, as I said before, some astronomers got the idea that they would like to actually take a picture as close as possible to this black hole and maybe even see this extreme bending of light or something like it. And this idea is the Event Horizon Telescope. It's a weird telescope. It's not actually like a big glass mirror, a big glass lens, or a big mirror, anything you might imagine a telescope would be. It's a radio telescope. So it's a bunch of radio dishes spaced all around the world. Okay, they're radio dishes or these microwave dishes in Antarctica. There are some in Hawaii. There's a really good one in the Chilean desert at Atacama. There's the very large array that if you've ever seen the movie Contact, famous array of radio dishes. And the neat thing about radio astronomy is if you take multiple radio telescopes and use them together in a synchronized fashion, These together form one giant telescope nearing the size of the Earth. And the bigger your telescope, the better your resolving power, the smaller an object you can actually take a picture of. And so the idea of the Event Horizon Telescope was to chain together these radio telescopes, observe simultaneously two different supermassive black holes we knew about, and try to actually get such a high resolution that we could kind of see the event horizon, the radius of the black hole itself. And so, as we look to the future, these astronomers hope to maybe even develop bigger radio telescopes, maybe put one on a spacecraft and have that orbiting away from the Earth so they can get an even larger effective telescope, and to take more observations to continue to sharpen this image up and teach us more and more about both the black hole itself at the center of our galaxy and the material around it.
Thanks for stopping by the Room of Lives today. Take care. Until next time.